All right, physics reaction video number 57. Here we go. This time I did a search for physics homework spelled out solution. Filter by this week, though. That really seems to do the trick. Here we go.
All right, so we're going to be getting into circuits. Our first circuit is a series circuit. So it looked a lot like putting springs in series, just one after another after another. This is an example of a series circuit with 3 resistors in it, okay? So to go from one end of our battery to the other, you have to go through each of those circuits.
So it looks like there's an autofocus thing going on every once in a while. Do you see how the image is going wonk, 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 wonk? I wonder if it's when he walks by, but it's certainly quite legible. Man, super good markers. I'm jealous. And it kind of looks like they erase remarkably well, too. Well, we'll see. So the very first thing he said, like putting springs together. So let's see, how much does my gut tell me? If you put springs together, it weakens them. Because basically you can stretch them all a lot easier because no single string are you stretching a lot. Whereas if you put springs in parallel, they get much harder. Think of that. When I was a kid, there was that thing where you stretched chest muscles and it had 3 big coils of springs here. So resistances, the R value, increases in series and goes down in parallel. So there's not a good analogy. I wonder how much he's going to stick with the spring analogy. So if he was talking about how much current is flowing and matched current to how hard it was to stretch the spring, well, yeah, that's a really interesting analogy. Certainly it looks like springs, right? So it looks like we're stringing them together. So maybe he's not going to go with that analogy at all, but he certainly got me thinking.
That's right. So looking at this diagram, let's talk about some symbols. All right. So these 2 lines right here, these 2 parallel lines, one long, one short, this represents your power supply, usually a battery. Okay.
Cool.
The long side is the positive, the short side is the negative. All right. And we draw current going from the positive end
Damn you, Ben Franklin.
to the negative end, which if you're thinking about what's actually traveling through those wires, seems kind of dumb. It's electrons.
It does seem kind of dumb.
Electrons want to go. They want to move away from the negative end of the battery and go towards the positive end. But that's not the way the conventional current is drawn.
Damn you, Ben Franklin.
Reason for that? Ben Franklin. He didn't know what electrons were, so he did his best. All right, so we draw our current line going away from the positive and going towards the negative, as if positive charge were flowing through those wires, despite the fact that it's actually negative.
I'm not actually sure what is causing the autofocus because it doesn't seem to be super tied to where he is. Just it seems like every once in a while it decides to refocus. I'm not 100% sure how those sensors work. I'm not sure if those sensors are really locational. You know, on my phone, when I take a picture, I can click on a single little face and it like rezooms to get the face in focus. So it does seem like it's able to look for sharpness in very small sections of the camera, as opposed to doing like a rangefinder. I don't think these things are doing range finding. I think they're looking for sharpness, but educate me if you know.
Negative charge, okay? Functionally, it makes no difference. None of your numbers will be different because it's traveling one way or the other, but if you have to draw a current, draw it that way, right? So, as this current's going through there, some of your energy is going to be used up by these resistors, okay? And what describes how much voltage and...
So I'm just looking at the clues that we have on the board here. I'm not 100% sure what's going on over here. There's a really interesting calculation going on over here. I'm not 100% sure what that is. But looking here, right, so I've been watching so many of these videos now that it actually strikes me that Kirchhoff's law is even written on the board right now, because often people will do the parallel and series tricks first, talking about what the equivalent resistance of resistors, and sometimes, frankly, not even drawing the battery. And then later they get to Kirchhoff's laws when they say, okay, let's string all these things together. So it's interesting that he's apparently going to jump right to it, which I think is what I do. But now, now I'm not 100% sure. I know that when I've worked on the parallel and series tricks before with students, I have insisted that we draw the battery every time because it helps me remind them, like, okay, well, what's this current doing? Rather than just a naked couple of resistors together and say, okay, well, these are two, just add them up, or two in parallel. Okay, just add their inverses. So I have tended to use the battery, and if I'm doing that, I'm probably talking about these two things, even if I don't specifically refer to them. The way he's talking up here, it's as if they've never seen a battery drawn before. I'm not sure if they've seen resistors before. He might talk about it here in a second. He's certainly talking about the direction of current. So this does sound like an early lecture. So we'll see how he jumps right into these guys.
How much current each resistor has are Kirchhoff's laws. Okay, so let's talk about those. All right. Now, the actual formulas that we're going to be making to solve circuits, to figure out how much current and resistance each resistor has, are going to change depending on how the circuit is set up.
Okay, so let's learn something about his camera. I'm going to go back about 5 seconds. There was a moment where everything seemed blurry. Here we go. Is there anything in the shot that's in focus right now? I mean, it doesn't look like it, right? So the board is blurry for sure. His face is blurry. His glasses are blurry. His hand and arm are all blurry. What would make the camera choose to go to this particular setting? Oh, wait a minute. His shadow is actually decent. And I was just thinking, if this was seeing the image of him, his image would actually be inside of the board. Maybe it's focusing on that. I mean, it didn't stay this way for long, but how frustrating. I mean, for him. It doesn't really bother me. Let me be clear. It doesn't bother me. I know what's going on. I can still read. But I'm so frustrated with these modern cameras that are trying to help too much. And in these cases, when we're just doing a static shot, I wish it was easier to shut off all this stuff.
Resistance each resistor has are going to change depending on how the circuit is set up. All right? Putting resistors in series makes things turn out one way. Putting them in parallel, which we'll talk about tomorrow, gives you a different relationship. All right? Kirchhoff's laws, they're the bread and butter. All right? No matter how we're setting these things up, Kirchhoff's laws will be followed. Okay? So, the problem solving that's required for solving a circuit, when we get to the really big ones, the weird ones, like combo circuits where you have things in series and in parallel together, it's less about knowing formulas and more about knowing these two relationships.
Oh, I like that.
Right?
Yes.
This is what's really important.
Yes.
Okay?
What he just said. Man, I got to pause and amplify that. What he just said. All of the rules, the little tricks that we learned, are relatively easily rederivable with these two laws, right? So the fact that series resistors add, the fact that parallel resistors add in inverses, all of it is actually super, super easy to just go back and use these two. In fact, I can be faster. I don't know. I mean, I really, really like what he said. Just back him up a little bit.
All right, this is what's really important. Okay, so let's make sure that we've got these really well understood. Because when I was in high school, I didn't get it. All right, I had a hard time with circuits. I really did. So I'm hoping that me having gone through that struggle, I hope that I'll be able to better address issues that might come up for you. And if you are confused as we're going through this, make sure to ask for help.
So I just want to pause for a second and talk about the motivation that he's using right now. He said, well, when I was in high school, I didn't get this, and I now see it's valuable, so I'm going to hope that you can learn it. And when I reflect on my career, I did an awful lot of that. Like, boy, man, this was so confusing to me. I really want to make sure it's crystal clear. But I'm struck by the incredibly common advice that, college professors get a lot. I don't know if high school teachers get this advice a lot, but college professors get this advice a lot, where it's like, don't assume that it's an audience full of you. You went on, you got your PhD, you're kind of in the 1% of caring about that material. If you're targeting yourself when teaching, you're actually missing the broader target. So, now that I'm in the dean's office, I kind of give that advice a lot, frankly. And so when I reflect on, ooh, man, this was so interesting and I didn't understand it until much later, I want to make sure that they understand it now. that feels good. It feels like a really great idea to do, but I do wonder how connected it is to that other idea of, don't just assume that everybody's like you. Usually that advice is about, hey, you might be aiming too high. Well, when I'm doing this, I want to make sure I explain it better. I actually feel like I'm aiming lower. I don't know. It's a really, really fascinating dynamic, and I'd love to get your thoughts about it.
All right, because circuits can be a rough unit if you don't reach out. Okay?
Cool.
It can also be really fun because there's lots of tactile
Turn them up a little bit.
engagement involved when we're actually making the circuit boards. Okay? So let's do this. All right, so Kirchhoff's first law. It says that the current entering a point will be the same as the current leaving a point.
Love it.
Right, so I like to think about circuits like rivers. Right? However much water is entering the river at the top is leaving the river eventually at the end. Right? And they split up in places, but the total amount of water at the end will be the same, right? Ignoring the fact that it goes into the earth. But so Kirchhoff's first law is basically
Ignoring the fact.
the sum of
Whoa.
current going into a point will be equal to the sum of the current leaving that point, the sum of the current going out.
Nice.
Okay. So if you've got something like splitting up, like if you've got
So Kirchhoff's laws are usually taught in tandem, and it's really, really interesting that, I was going to say that Kirchhoff's first law is not super useful in series circuits, but I guess it is, right? Because you can really say, well, look, it's not like it can possibly be used up. You must have the same current here as here as here as here as here. So I guess it is going to be useful. But I guess I was thinking that it's the workhorse for parallel circuits. So yeah, it makes sense to do them both right now. This way. I also have really, really liked his language. What goes in must go out. It's going to help him, I think, with the directionalities that he's going to have to deal with. And I think it's really going to help him with the series circuit too. Also, really, really interesting that today is series, tomorrow is parallel. Like, very clear. We're going to really carefully build this up.
I don't know, like 5 amps of current going into a point.
That's a lot.
Right? And I know that I've got 1 amp of current going over this way, 2 amps of current going over this way.
Two.
All right, if I'm looking for that current in that middle point, I don't need to measure it. I can figure out what it is just mathematically. I've got a total of 5 amps going into this point. So that means a total of 5 amps needs to be leaving that point as well. I've got 1 going that way, 2 going that way. So all that's left would have to be going through that middle path. So this would have to be also 2 amps going this way. And the amount of amperage going through each path is just based on how much resistance there is. So looking at this, this path would just have more resistance, right? There's less current going through, so it must be resisting that current traveling, all right? But if you add all of your current going out, it will always equal your total current going into a point, all right? So that's his first law. Second law says that the sum of voltage drops is equal to the total voltage between 2 points. Okay, so sum of voltage drops. So this is just the voltage that's used at each point. Again, I still like to think about a river, but instead thinking about like waterfalls. Okay, you take water and drop it off a waterfall, it is going to lose potential energy. Right? It has a lot of gravitational potential at the top of the waterfall, and that becomes kinetic energy at the end. Right? You have a lot of.
So it's such a common analogy, and I love it from the perspective of, that you're going to lose, you have to add up how much you lose. The problem in circuits, of course, is that there's such huge amounts of, I was going to say friction, that's probably the wrong word, but there's basically no kinetic energy gained, right? These poor electrons, they don't get to run, right? So I'm going to watch for that. But I'm really liking the way he's setting this up, right? He's not talking about going around a loop. He's talking about look at a drop and compare to how much, it would have taken to get back up there. So he's like breaking the normal loop way of thinking about Kirchhoff's second law into the drops and the rises as separate things, which I like. I've got a blog post, maybe I'll connect it down below. I think it's titled something like "I Hate Kirchhoff's Loop Law," and you'll see the way that I teach that stuff.
Electrical potential within a battery or a power supply, and allowing it to go through resistors, that potential energy is used up. All right. Each waterfall or each resistor that the current goes through, you lose more voltage, more potential for energy. Okay, so the sum of all those potentials that are lost is equal to the total voltage along that path. Okay, so let's look at an example.
Total voltage along, kind of caught my ear, but I get totally where he's going here.
These 2 points in the circuit, my total voltage is 3 volts.
Okay.
So that's like, I've got the top of a waterfall, I've got the bottom of a waterfall, I've got a certain amount of energy to gain. Okay. Now let's say that along one path, okay, so there are 2 resistors. All right, so kind of think about this like we've got 2 separate waterfalls. It goes along this path, uses some of that energy, goes along the path, uses some more of that energy. Each one of these is like another waterfall. But in getting to the bottom, you still lose the same amount of potential energy. Right? If we have 3 volts across these 2 points, some of it's going to be used there, some of it's going to be used there. And the amount that's used is based on how much resistance it has. Okay, so let's say this one had 1 volt, it was using up that much energy. The rest of it would be used up by that one. Okay. Little waterfall, big waterfall. Okay.
Cool.
But sometimes it isn't just going down one path to get from one end of a battery to another.
See, this I thought he'd wait till tomorrow.
Waterfall to another. Right. There may be 2 separate waterfalls next to each other. Right? It doesn't matter what path we take. To get from this point to this point, we have 3 volts of potential.
Yeah, like that.
So much height on our waterfall to use. Right? Going from the top to the bottom, we're losing the same amount of potential no matter what path we take down the mountain. Okay, so this way,
I like that.
If we take this path between these 2 points, we've still got 3 volts.
It seems like it's a little bit off because today's supposed to be series day, but man, this is setting it up for tomorrow.
Resistor, which means that all of our voltage needs to be used by this one resistor. All right. So, a rule: the total of the voltage drops, the sum of the voltages used by each resistor along a path, will always equal your total voltage.
Yeah.
Okay. We'll talk more about this sort of circuit where you got it branching off when we get into parallel circuits. But these are the 2 laws that we're going to be using to solve series circuits today.
Cool.
Okay, so let's actually get some formulas in here so we can start.
Okay, so what happened there? A break. He erased the board. He rewrote some stuff. Yeah, great savings of time, right? Some post editing that had to get done. It's not the end of the world to show people erasing the board, but okay, very cool.
Calculating some stuff. All right. So we've got a little simple circuit. All right. Sometimes instead of drawing like the whole circuit in here, like with the wire connected
I was wondering.
with the positive and the negative end, I'll just draw these 2 dots. Right. That represents the positive end and the negative end of your battery. Okay. It'll be flowing from one end to the other. Just takes up less space.
Man, that's a great eraser. What is he using? Holy cow, that's
Let's say we want to
amazingly
look at
clean.
the current relationship here. Okay, our battery will have some total current. Okay, which you can find using voltage and resistance, looking at Ohm's law. Right, V equals IR. You can solve that for I. Okay, and that's always the first thing I would do. When looking at a circuit, just find your total current. Your total current is just going to be equal to your total voltage over your total resistance. Okay, and we'll talk about how to find that total resistance in just a second. But you can use this for any formula, or for any circuit, as long as you know your total voltage, which you probably will, because you know what batteries we're attaching to stuff, and total resistance. There will always be a way to find that, which we'll talk about later. All right, so always find total current first. It's very useful because it starts telling you the relationships between stuff.
I like that. Good
We'll always
scaffold.
end up needing that. Okay, but what if we wanted the current through one of those other points? Like, what if I only wanted the current going through resistor 3? And like, I've got a couple electronic devices hooked up in series to each other, and I want to figure out how much current my toaster's getting. Okay, we can find that using Kirchhoff's law. Okay, so we've got some total amount of current. Let's just give it a number so we can attach ourselves to it. Let's say that we've got 3 amps of current going through here.
It's a ton.
Okay. All of that current has to somehow get from the positive end of our battery to the negative end. It all has to go from one end to another. Right? If it doesn't have a clear path, it doesn't travel. So it has to go through the circuit somehow. All right? So going from one end of a battery to another. When it reaches R1, there aren't any other pathways for it to go through. That entire 3 amps of current has to go through resistor 1. Okay? So what we can say is that our total current is equal to the current at 1. It all has to travel through there. Okay? So it's all gotten here. It's got to continue traveling. When it gets to resistor 3, there aren't any other branches. It
Love
still
that.
has to travel through there.
Love
It's
that.
like putting 3 points on a river. This river isn't branching off anywhere, so all that water has to go through every single one of those points. Okay? So it would also be equal to however much current you have going through resistor 2. Okay? Once it's done going through resistor 2, it comes to resistor 3. It still doesn't have another branching path. It still has to get from one end
Man.
to another.
I just love how thorough he's being.
To get to the other side, it has to go through resistor 3.
I mean, I'm just going to pause here.
So when you're looking at resistors in series,
Right, I can just imagine what this would have been like if he had had a live audience, right? Live students in his classroom. I don't think that he would have done that, said all of that. I think at some point he would have said, "What is that? Does anybody have a thought about what happens to R3? Should what do we use a different argument for R2 than we use for R1?" So, but his thoroughness here was great. I think that the students who are like, "Huh, what? I hear him say it again," right? Can get that light bulb going off. I suppose you could stay lost, but I really think he did a great job with that. Just looking at the time, I think I'm going to stop here. I just want to talk about there's some really, really great things that are happening. I really loved his approach to Kirchhoff's laws. It wasn't sort of standard. Like the loop law wasn't written as a loop. So check my blog post that I'll post down below to see my frustration with it. And I think that the way that he was talking about the sort of setting the table for parallel tomorrow was really, really cool. That should be ready to roll when he gets to that. And I think that he was just really, really careful about a lot of things. Like, well, normally we don't draw the battery, but remember there is a battery here. That was really cool too. All right, everybody. Well, have a great day. And remember, physics teachers are awesome.